Hi everybody. Let's continue talking about the INH, and now we will just focus on the SAR or the structure activity relationships for this antimycobacterial drugs. And as we know that the structure of isoniazid, it is the isonicotinic acid hydrazide. So the only possible modifications that have been done to this structure is by modifying the R1 here and R2 or R3. In general, most of the derivatives of isoniazid were not superior in activity. So many derivatives have been prepared, but unfortunately none of them were more active than isoniazid. Because of that, they did not reach the market. So still the isoniazid, it's the major drug from this group. Okay, but in general, the R1 here must be H. And if it has been modified by different alkyl or aryl moiety, these derivatives were almost inactive. While R1, R2 and R3, they can accept alkyl group and in general small alkyl group, not bulky, and it has retained the activity, but it did not show improved activity. So this is all about the SAR of isoniazid. Let's now talk about the metabolism of isoniazid, because the metabolism it's responsible for the toxicity of isoniazid, unfortunately. And we will just mention one metabolite, which is the acetylated metabolite. So here we have the acyl transferase enzyme, which is available in our body. It will metabolize this compound by adding acetyl group to this nitrogen atom. In this case, we will have this compound, which is one of the major metabolite for isoniazid. And as we can see here, we have the acetyl group added to this compound. This compound will continue the pathway, because this group will act as a leaving group, and we will end up with what is called the acetyl hydrazide. And in this case, the hydrazine moiety, it is a good leaving group in most of the organic compounds. And after that, the final product will be the acyl radical. In this case, the acyl radical, it is the toxic metabolite, or the final toxic metabolite. This acyl radical will acylate liver proteins. So let's just put a liver protein as a B, which will act as a nucleophile, or even it can form a radical in a normal radical reaction. So it will be acetylated by this toxic electrophilic species, and we will end up with acylated protein. Of course, acylated protein will be non-functional protein. So non-functional means toxicity. So it's very important to monitor the patient for possible liver toxicity. So by time intervals, so we must have a liver function test just to make sure that everything is okay and there's no toxicity or possible toxicity from isonicotinic acid hydrazide. Okay, let's stay on talking about the metabolism of isoniazid, and as we can see here, we said that the enzyme responsible for this is called the acyl transferase enzyme. This enzyme, we have individual variations in terms of this enzyme. Why? Because for this enzyme we have what is called a polymorphism. A polymorph. What do you mean by polymorph? It is more than one shape or isoform from the same enzyme by having a minor or minimum structural modifications. So still this enzyme is acyl transferase, but it has been mutated, has been modified. So we have individual variations in terms of the availability of different isozymes or isoforms from this enzyme. So in general, we have two types of polymorph or isozyme. We have a rapid. So individuals can be divided into two major types or phenotypes: rapid acetylator and slow acetylator. So in the case of rapid acetylator, here this individual or this patient will rapidly acetylate, so rapidly acetylate isoniazid. In this case, isoniazid will be converted very rapidly to the toxic metabolite, right? So it will be rapidly converted to toxic metabolite, and this patient will experience toxicity very rapidly. So we must know which phenotype is this patient in order to make sure or to predict the possible toxicity of isoniazid. While in slow acetylator, here isoniazid will not be converted very rapidly to the toxic metabolite. So in this case, the toxicity will not appear in a short period of time. So maybe it will appear later. So it's very important here to know the phenotype of the patient, whether it is a rapid acetylator or it is a slow acetylator. Okay? In general, this is all about the structure and reactivity and metabolism of isoniazid, and we should know that isoniazid is relatively toxic to the liver, and it has some toxicity to the CNS. So it's very important to monitor the patient for possible toxicity. Although it is relatively toxic, especially on the rapid acetylator, it is still one of the mostly effective anti-mycobacterial agents found in the market. In general, isoniazid, it's not given alone. it's normally given in combination. So just to make sure that there is no resistant cases, and this combination will overcome the possible resistant mechanisms for isoniazid. So in general, almost all antimycobacterial agents, they are normally given in combination rather than monotherapy. Why? To overcome the possible mechanisms of resistance. Okay, let's start talking about another member of antimycobacterial agents. It is the ethionamide, and as we can see here, it is closely resemble the structure of isoniazid. Ethionamide, again, it is effective antimycobacterial agent, and it is bactericidal, especially on the growing TB. It's not active against the dormant or the persistent TB. So it's not be able to penetrate the macrophage to reach the persistent pathogen. It is relatively toxic again. So it's toxic to the liver, it's toxic to the CNS. So in most of the cases, it has been stopped from using as anti-TB drugs, but still in some cases, especially when a resistant cases has been found to isoniazid or other antimycobacterial agents, we can still use this compound. Okay. Regarding the SAR of ethionamide, relatively it has almost the same mechanism of action as isoniazid, so it must be activated. It will give what is called a radical formation that will form an adduct with NADH. So without forming an adduct with a NADH, it will not be able to inhibit the INHA enzyme that is found in the Fas2 system. So it is very important to for ethionamide to be activated inside our body and inside the mycobacterium. There is an enzyme catalyzing this. It is called ethionamide oxidase enzyme that is very essential for the activation of ethionamide. In this case, if this enzyme has been deleted or corrupted or mutated, the ethionamide will not be able to kill the Mycobacterium TB. Okay? So it must form an adduct. And in this issue, I just want to talk a little bit about this inhibition and how isoniazid and ethionamide must complex with NADH in order to inhibit this enzyme. So in general, if we are talking about enzyme inhibitors, so we have either enzyme inhibitors, we have either a competitive or non-competitive. And we will not talk about the non-competitive or the allosteric inhibitor. We'll just focus on the competitive inhibition. What do we mean by competitive inhibition? Competitive inhibition means to to design a drug that will bind to the same binding site or the active site for the enzyme. So if we are going just to draw a representative drawing for an active site for a given enzyme, or let's say it is the INHA enzyme, which is our target. And as we know, most of enzymes, they will not work without a coenzyme. So for example, INHA is a reductase enzyme. So what do we mean by reductase? It will catalyze a reduction. If we are talking about a reduction, so this enzyme will not work without the NADH, or other reductase enzyme, they will not work without the FADH or NADPH, and so on. In our case here, INHA will not work without the NADH. NADH, it must bind, let's say, here, because most of the coenzyme, they will bind to the same binding site of, or the active site of the enzyme. So here it is the pocket for the NADH structure, and the substrate will bind here. Because of that, we are talking about the catalyst, or the catalysis of the enzyme that will serve as a surface for the reaction to take place between the coenzyme and the substrate. Okay? So in this case, you have relatively three options to design your inhibitor. Whether it will mimic the structure of the coenzyme. So I will prepare my drug, I will design my drug to mimic or to have similar structure to the coenzyme. In this case, it will bind to the pocket of the coenzyme and it will inhibit the action of this enzyme. Or I will prepare it to mimic the structure of the substrate. And most of our enzyme inhibitors, they are mimicking the substrate. So they will bind to the substrate. In this case, they will inhibit the action of this enzyme. Or I can prepare my drug or design my drug to mimic both of them. So in this case, I will prepare it to have similar structure to the substrate in addition to the NADH. But which option is the most suitable option to inhibit a given enzyme? First of all, let's talk about the drug that will mimic both of them. In this case, in order for my drug to mimic both of them, in general, my drug will be a bulky structure. So it will be very bulky. In this case, I will end up with problems in pharmacokinetic. I will end up with problems in, for example, absorption, in distribution, in getting into the Mycobacterium TB. So it has so many complications to have a bulky structure for your drug. So this is not an option in most of the cases. While to mimic the structure of coenzyme, it is possible, but in this case, it will be non-selective because NADH, it's not a coenzyme for INH only. It is a coenzyme for most of the reductase enzymes. You see? So, if isoniazid will inhibit the INHA, it might inhibit other reductases inside our body. And we will end up with side effects and toxicity. So, it is possible, but we might experience toxicity. So, in general, the most active and selective way of inhibiting the enzyme is by targeting the substrate pocket. Because this substrate is selective for this enzyme. So if we are targeting or designing my drug to be similar to the structure of the substrate, it will be only targeting this particular enzyme. In the case of INH, it's not mimicking the structure of the substrate, it's not mimicking the structure of the coenzyme NADH. Because of that, we were talking about activating INH inside the mycobacterium by enzyme called CAT-G. And we said that INH will combine with NADH to form a complex, and this will be done by enzyme called CAT-G, which is available inside the mycobacterium. In this case, this complex will mimic the structure of the coenzyme, and it will bind to the NADH pocket. You see? So INH is a prodrug, and in this case it is called a bioprecursor prodrug. Without complexing with NADH, it will not be able to bind to the NADH pocket of the INHA enzyme. Okay? We'll stop here and we'll continue talking about the rest of antimicrobacterial agents in the next lecture.